Perfect. All right. Welcome everyone to today's GOCC meeting. Today we have Yichen Ma, and she's going to be talking to us about invariants of partial orders and convex geometries via characters on Hopf monoids. Before we start, I want to remind everybody of our community agreements. We are all learning. Everyone has something to contribute, and no one has all the answers. If you have questions, feel free to interrupt, or you can write them in the chat, and one of the organizers will share them with Yichen. So Yichen, you don't have to watch the chat if you don't want to. We'll make sure you get the questions in there. And with that, Yichen, welcome.
Okay, so thank you for introducing me and give me an opportunity to share what I'm interested and what I'm doing. So don't worry if you do not understand the meaning of the words in the title, so I will introduce all of them later. So the goals for this talk are mainly three parts. So first, we want to describe certain polynomial invariants of partial orders and convex geometries in a unified way. So specifically, we'll reintroduce some famous polynomials. For example, ordered polynomial, strictly ordered polynomial, enriched ordered polynomial, and so on, in the perspective of characters. And then we want to unify a collection of reciprocity results for the above polynomials. So different authors obtain those reciprocity results from different ways, but we will unify the way of this result by characters and polynomial units, specifically the properties of characters. And finally, we want to describe a more general quadrisymmetric invariance. So we want to describe the coefficient of the invariance by combinatorial and geometric representations. And specifically, some of them satisfy some very nice relations. So for example, Bayer-Villar relations, and we'll show that. Okay, so in my talk, I will define two Hopf monoids. So one is the Hopf monoid of partial orders, and another is the Hopf monoid of convex geometries. And each of them will discuss a collection of characters. So first, we'll define a canonical character, eta, which sends every basis element to 1. So this is the simplest. And after that, we'll determine the inverse character associated to eta bar. So I will define what eta bar is. It's another simple notion. And after that, we'll define a pair of characters, phi and phi prime. So they're called it odd, means they're satisfying some nice properties. And I will also give an introduction on that. And after all, we'll determine the two invariants associated to this collection of characters, specifically a polynomial and a quadrisymmetric function. Okay, so before all of this, let me give a brief introduction of the things in my title, Hopf monoids, characters, and invariants. So a Hopf monoid of H consists of the following information. So first, for each finite set I, we have a vector space. And then we have two linear maps. So first, you can call it product or multiplication. And secondly, the co-product or co-multiplication. So these maps are defined for each finite set I, and each decomposition I equals to S and T. So these operations satisfy some simple axioms, and they should be compatible with each other. So I won't go over the details of those axioms, but you can also think about the Hopf monoid as a functor from the category of finite sets to the category of vector space, satisfying monoidal, co-monoidal, and some compatibility axioms. So for today's talk, we assume the Hopf monoids such that when we applied H on empty set, we obtained some field K. So let's see an example, the Hopf monoid of partial orders. So for each finite set I, we'll let PO be the vector space spanned by the set of partial orders of I. So for example, if I equals to the set containing two elements, then this POI is the vector space spanned by the pole set with no partial order without relationship between A is less than B, and B is less than A. And on this set, we define two operations. So the product is defined by disjoint union of P1 and P2. So if P1 is A less than B, and P2 is, for example, CDE, then the disjoint union P1, P2, I write it as a parallel sum. This is simply, we just put them together. Okay, without adding more informations. And the coproduct is defined by a tensor product of restrictions if S is a lower set of P and zero otherwise. So indeed, those operations are defined on the basis elements of POI. So to obtain the general operations, we only need to extend the multiplication and the co-multiplication linearly. So indeed, this POI with the multiplication and co-multiplication admits a Hopf monoid structure. Okay, so if we have a Hopf monoid, we have a notion of character. So indeed, a character C is a collection of linear maps determined for each finite set I. So it sets HI to our field K. So it satisfies the following axioms. So if I is an empty set, then C sends 1 to 1. And also it preserves the multiplicity product. Okay, and this is defined by decompositions of I. So there's a well-known theorem of the characters on the Hopf monoid, that is the set of all characters for given Hopf monoids form a group under the convolution product. So the convolution product is also defined by as a sum runs over all the decompositions of I. So length 2 decompositions of I. So we first do the co-multiplication and then we compute the tensor product of the character. Okay, so in this group, the identity element, we also call this unit. This is the character epsilon defined by if I is an empty set and x equals to 1, then this epsilon sent 1 to 1. And this is a zero map when I is a non-empty set. And the inverse of a character C is C composed with S. So here S is an antipode of H. So the antipode is something specifically for a Hopf monoid structure. So a bimonoid structure may not contain an antipode. And computing the cancellation-free formula for an antipode of a given Hopf monoid is an open problem for many Hopf monoids. So I won't explore this too much in this talk, but just keep in mind. Okay, and then let's introduce the polynomial invariant. So now we fix a Hopf monoid and see a character. And then the polynomial invariant is a function from the natural numbers to our field K. Still, we're running a decomposition of I, but now where the length of the decomposition is n, so it depends on the natural numbers. And we first do the coproduct or the iterated coproduct, and then we apply the characters, the tensor product of the restriction of characters of each part of the decomposition. So a proposition which we can obtain from direct computation is that this invariant is indeed a polynomial function of n. So that's why we call this polynomial invariant. Okay, so since this is a polynomial on n, we can evaluate this polynomial on negative integers. So I will introduce how we evaluate in the next slides. And also, this is indeed an invariant of a structure X because isomorphic structures will yield the same polynomial. So for example, if we have on the pole set, the Hopf monoid of pole set, if we fix a set I, we have x1 and x2 have the same shape, even, oh, they're the same. So I put C here. Let me do it again. Okay, so even though they have the different labeling, since they have the same structure, they yield the same value in the polynomial invariant. Okay, so just like what I said, I will introduce how to evaluate the polynomial variant on the negative integers. Okay, so first, if we have a character c, then we can define another character c bar by applying -1 to the size of I to c. So then we have a general reciprocity result for the polynomial variant. That is, if we want to compute the polynomial evaluated on -n for c, then we only need to know what's happening on the convolution inverse of c bar. So this is general, but this is definitely not working well in many cases. So for example, for many Hopf monoids, it's hard to compute a cancellation-free formula for the antipode. So for general characters, this is just a result, but not very useful in computations. However, it turns out there's a class of characters for which it is easy to compute the polynomial variant evaluated on negative numbers. So that's are the odd characters. So we say C is an odd character if C and C bar are inverse in the character group. And indeed, we have self-reciprocity for the polynomial variant of odd characters. That is, if we want to evaluate the invariant on negative numbers, we only need to know the size of the ground set I. And for any characters, we're able to determine a pair of odd characters. That is, we can compute the convolution product of C and C bar inverse, or the convolution product between C bar inverse and C. We change the direction, and both characters are odd. Okay, so now let's determine the first example and the most specific examples on partial orders. So on this Hopf monoid of partial orders, we can define 4 characters: eta, zeta, phi, and phi bar, and phi prime. So the simplest is eta, so for which we just send every basis element to 1. And then we're able to determine the convolution inverse of eta bar, which we call it zeta, and we'll let phi be zeta composed with eta, and phi bar, phi prime be the eta composed with zeta. And then all of them have nice combinatorial description. So zeta sends p to 1 if p is an anti-channel I, means there are no relations in p, and 0 otherwise. And for phi, this is 2 to the power of the number of minimum elements in p. And for phi prime, this is 2 to the power of the number of maximum elements in p. So for example, if p is this ABC, then phi IP is just 2, and phi prime IP, this is 2, 2, 2, and this is 4. Okay, so with the notion of eta and zeta, we're able to reintroduce the order polynomial. So first, we let the single bracket n be the linearly ordered set of all elements from 1 to n. And then by computations, we know the polynomial variant associated to eta counts the number of order preserving maps. And the invariant associated to zeta counts the number of strictly order preserving maps. And we know this notation from Stanley. So indeed, these numbers are order polynomial and strict order polynomial. So Stanley obtained a reciprocity between these two numbers, between these two countings in his own way, but we can also retrieve this result by the fact that eta bar is the convolution inverse of zeta. So then we have the Stanley's reciprocity. Okay. If we consider the cases for phi and phi prime, then we're able to retrieve the enriched order polynomial introduced by Stanbridge. So now we consider the double bracket of n. So you can think of this as an ordered version of a single bracket n with a signed copy. So then if we compute the polynomial invariant, the invariant associative phi counts the number of certain order preserving maps. So first, it should be order preserving. And we also have the fact that the preimage of I bars are anti-chains for all i's. And we have another counting for phi bar. So this invariant counts the number of order preserving maps such that the preimage of the unsigned value I is an anti-chain for all I. So indeed, Stanbridge discussed these countings in his paper in 1997, and these are indeed the Stanbridge enriched order polynomials. And he also gave an argument on the reciprocity result for those polynomials, and we can retrieve this result by the fact that phi and phi primes are both odd characters. Okay. So before I go to the part of convex geometries, I want to first describe a more general definition of the closure operators. So since we have a very nice relationship between partial orders, convex geometries, and closure operators, I want to describe this broad picture at first, and then we go to the specific discussions in the convex geometries. Okay, so first we let 2 to the I denote the power set of I. And then the closure operator is a map from the power set of I to itself, satisfying the following axioms. So first, given any subset A of I, A is containing the closure of itself. And second, if A is containing a closure of B, then the closure of A must be containing the closure of B. And if we have some set K such that the closure is itself, then we call it K is a closed set. So a nice thing for closure operator is that the closed set of a closure operator constitute a lattice. And for the purpose of our talk, we assume all the closures are loopless, which means the closure of the empty set is just the empty set. So we have a little information about the lattice. We know the minimal element is the empty set and the maximum element is I. So in general, we don't know what happens on the lattice, but in the setting of some well-known closure operators, for example, matroid convex geometries, pole set, we know many nice information about the lattice. Okay, so given a collection of closure operators, we can actually define some new or construct some new ones. And I want to describe these specific operations which leads to a Hopf monoid of closure operators. So first, we consider a decomposition of I, which we denoted as in T. Then if we have closures on S and a closure on T, then we can define a direct product of closure operators. So we can regard this statement as the closed set on the direct product is simply the sum of the closed set of each one. And if we have a closure E on the set I, then we're able to determine a notion of restriction and a notion of contraction on S or on T. So for the restriction, we just restrict the things on what's happening. We just restrict the operation on A. And for the contraction, if we have some B in T, then we first compute the closure of B union S, and then we minus S, where we intersect the result with T to guarantee what we obtain is in T. So if we check the axioms, we're able to get the result that the direct sum, the restriction, and contractions are all closure operators.
We have a question in the chat that I shared. For our sum operator here, what is the sum of the sets?
Oh, so for example, A plus B is just A union B, where A is in A and B is in B. Does that make sense?
So this is distinct from the union because we're summing sets of sets?
Yes.
And so we're getting, okay,
Yeah,
I
so we're,
think-
yeah.
I'm following. I'll let the person who asked the question. Okay, yes, we're all good.
Okay, good. So, yeah, so as I said, we have some other closure operators from the old ones. And it turns out we have Hopf monoid of closure operators from the operations we introduced in the previous page. So for each finite set I, we let COI be the vector space with the basis the set of all closure operators on I. So then it turns out this CO is a Hopf monoid with the product as the direct sum and the coproduct defined as the tensor of restrictions and contractions if S is closed and zero otherwise. Okay, so these operations with the definition of the vector space gives us a Hopf monoid structure. Okay, so then we have a general picture of what's happening on the characters of closure operators. So still, we can follow what we did for the pole set. We can define 4 characters. So first, we can define phi eta to sending every basis element to 1. Then we have zeta, phi, and phi prime. So indeed, we can determine an expression of zeta. That is, if for any closure C on I, this zeta C is -1 to the size of I times the value of a Mobius function on the interval from the minimum element to the maximum element. So this Mobius function is with respect to the lattice of the closed set of C. Okay, so usually this zeta can be complicated, or it just can be very mystic because we do not know what's happening on the Mobius function because of the varieties of lattice. But in many cases, so for example, for convex geometries, we have the result that the closed set of convex geometries corresponds to a semi-distributive lattice. So, a mid-distributive lattice. And for this lattice, we have some nice result. And for pole set, we also have the lattice is distributive, so we can determine zeta in an easy way. Okay, so we'll follow this procedure and we'll discuss the results of zeta, phi, and phi prime in the special case of pole set and convex geometries. But before we go that, I want to say the importance of the closure operators as in general. So this is because besides anti-matroid convex geometries or pole set, we also have matroid. This is another collection of closure operators. So let I be a finite set, then we know a matroid is a closure operator satisfying the exchange axiom. And then if we change the statement in the exchange axiom a little bit, then we would able to get the anti-exchange axiom. And then we are able to get the anti-matroid or convex geometry. So this is a closure operator satisfying the anti-exchange axiom. So a closed set of a matroid is called a flat, and a closed set of a convex geometry is said to be convex. So it's just for notation. So we have some nice result for matroid or convex geometries. So for matroid, the flats constitute a geometric lattice, and for convex geometries, the set of all convex sets constitute a. I think there's a typo here, so it should be a mid-distributive lattice. So which means if we have AB where A is covered by all the elements that B covers, then the interval AB is a Boolean algebra. Okay. So in my talk, I will focus on convex geometries. And there's a nice picture of convex geometries which illustrate the anti-exchange axiom. So for example, if we have an arbitrary set A, then we know the convex hull of A is this graph, and we have Y is contained in the convex hull of A union X, but by the anti-exchange axiom, X cannot be contained in the convex hull of A and Y. So this is a nice illustration of anti-matrix. So you can, in a non-discrete setting, you can regard this convex geometry as convex Hopf. Okay, so why do I care more on convex geometries in this talk? So this is because convex geometries generalize the notion of partial orders. Indeed, if we have a partial order P, then we're able to determine a convex geometry GP directly from this P. So indeed, for a subset A of I, GP applied on A is all the elements in I such that this X is bounded by some elements in A. So then we have the convex sets of GP are indeed the lower sets of P. And since the lower set of a pole set constitute a distributive lattice, the lattice of convex geometries induced from P of lower sets is also distributive. So there are nice relationship between the Hopf monoid of partial orders, convex geometries, and the closure operators. So indeed, the convex geometries constitute a Hopf submonoid of the closure operators, and partial orders constitute a Hopf submonoid of convex geometries. So we have this nice map. So indeed, since we have the 4 characters defined on closure operators, we can deduce these characters to the convex geometries and the pole set. So we have discussed the partial order cases in the previous slides. Okay, so let's continue the discussion of characters on the convex geometries. So recall, for this eta, send every basis element to 1. We have the convolution inverse of eta bar on pole set setting. This send P to an anti. This send P to 1 if P is an anti-chain on I and 0 otherwise. So by computation, we could obtain the zeta on the convex geometry setting. So this zeta send G to 1 if G is the identity operator and 0 otherwise. So the identity operator means G send every set to itself. So you can also regard that G is discrete. So you can either compute the result from the notion of characters, or you can simply get the result from the knowledge of Mobius function of a mid-distributive lattice, or vice versa. Okay, so I made a typo here. And the result for partial orders can also be obtained from the expression of Mobius function of a distributive lattice. So indeed, we have the fact that the Mobius function on an interval on 2 elements is 1 if the interval is a Boolean algebra and 0 otherwise. So that's the main idea. Okay, so with the knowledge of eta and zeta, we're able to discuss the pair of odd characters on convex geometry. So first, let me do a definition. So a subset K in I is called a totally convex if subset of K is convex. So you may also, using this definition, we may rewrite this as if I is a totally convex set with respect to G. And also we have notion of extreme points. So extreme points of G is some element such that if we minus X from our ground set I, then the remaining subset is convex. So with these definitions, we have a nice description for phi and phi prime. So indeed, phi applied on G is the number of totally convex subset of I. And phi prime of G is 2 to the power of the number of extreme points in G. And this is also the number of subsets of I consisting of the extreme points. So then we're able to derive the ultimate Jamison polynomial. Before that, let me introduce what this polynomial described.
Before we proceed, can we go back a slide quickly?
Yes.
So every totally convex subset is going to be a subset consisting of extreme points, but a subset consisting of extreme points isn't necessarily totally convex, because you can you can go down one level and you'll stay convex by removing any element, but if two elements.
So totally convex set does not contain extreme point. So it is not a set containing extreme point.
But if you're totally convex, then the subset of just removing one element would be convex, right?
A subset with, yes.
So
okay, so
ABC is totally convex, then the set BC is convex, right?
So let me share an example.
Yeah.
So we let G be the convex geometries on the 3 collinear points, right? Then B is a totally convex set. You agree?
Yes.
But B is not an extreme point, since the convex whole of AC is the whole thing. So let me write it. Yeah.
I was misunderstanding the definition of extreme point. Got it. Okay.
Okay. So for this case, for this G with 3 collinear points, the extreme points is just 2 because it consists of A and C. Okay. So that's the difference.
Thank you.
Indeed, yes. So indeed for phi and phi prime, we're counting different things. And indeed for phi, we do not have a nice description as phi prime. So this is not a power of 2 always. Okay. So before we go to the element Jamieson polynomial, let me introduce the notation of a function to be extremal and strictly extremal. So indeed, these are a generalization of order and strictly ordered polynomial. So first, we let G be a convex geometry and let f from I to n be a function. So f is an extremal function if for each convex set K, there exists some extreme point for G restricted on K, where f restricted on K achieves its maximal value. So I will give an example after I introduce the strictly extremal function. And f is called a strictly extremal if for each convex set K, every point where f restricted on K achieves its maximal are contained in the extreme points of K restricted on K. So let's see an example. So we still let G be this collinear points, and N be 2 elements. And we let A send to 2, B send to 1, and C send to 1. And then this is an extremal function. But this is not a strictly extremal because this is an extremal function. Let's see another function. This should be a strictly extremal function. Okay, indeed, I think the first one is also a strictly extremal. So let's see. Yes, never mind. So bad example, but I think what I gave 2 strictly extremal functions in this case. But there are slightly difference between the extremal and the strictly extremal functions.
Would the function 2, 2, 1 be extremal but not strictly extremal?
Let's see. Yes. Okay. Yeah. I think that's a good example. Yes. So let A goes to 2, B goes to 2, and C goes to 1. Yes, because then B reaches its maximum value, but this is not extreme. Yes. Thank you. So this is a example where f is extremal but not strictly extremal. Okay, nice. Okay, so the idea is that if we compute the polynomial invariant, then the invariant associated to eta counts the number of extremal functions, and the invariant associated to zeta counts the number of strictly extremal functions. And indeed, those countings was first introduced by Elderman and Jamieson, and by the argument of the character, those invariants are indeed polynomials. So Elliman and Jamieson obtained a reciprocity result between the number of extremal functions and the number of strictly extremal functions. And we could retrieve this result by the fact that phi bar is the convolution product of Z, convolution inverse of Z. Okay, so for phi, we also have some nice description of functions, but since this does not correspond to like any well-known literatures right now, I won't go over it in details. But for phi prime, we have some nice description from the existing literature. So recall that the double bracket n denotes the order set, this order set, and then we have the invariant associated to phi prime counts certain number of extremal functions. So first, it is extremal, and in addition, it must satisfy the following property. So if we have some a such that the value of fa lies in the onside part of n, so this is not any I bar, but it's just I, then a must be an extreme point in G restricted on the set of or B such that FB is less than or equal to FA. So let's see an example. So still, we let G be this convex geometry on 3 collinear points. So why do I like this convex geometries a lot? This is because this is the only one convex geometries of 3 elements, which is not from any partial orders. So now we let n be just 1, the double bracket 1. And then we let a goes to 1, b goes to -1, and c goes to -1. And this is an example of the functions that we're counting by phi prime. Right. Okay, so
do you mean 1 bar? Or
yes,
you mean
yes,
1 bar? Okay.
1 bar, yes. So yes, so idea is that we're doing some signed version of n. So okay, so this counting was first introduced by Blair, Rachel, and Proven, and they obtained the reciprocity result for this number. So we can obtain this result from the fact that phi prime is an odd character. Okay. So I think I have 10 minutes left, and in the last 10 minutes, I want to introduce the quadrisymmetric invariant and some nice geometric and combinatorial connections of this invariant. So first, let us fix a Hopf monoid H and see some character on H. And we'll let I be some finite set. So we know, so let us recall the composition. So this is, okay, so we know the definition of compositions, and then we define some F values with respect to C and a composition F. So to determine F, first we compute the coproduct with respect to this composition, and then we applied a tensor product of the character C restricted on SIs. So for example, if H is the Hopf monoid of convex geometries and F is a composition of less 2, then this F value is simply we first applied C restricted on S to G restricted on S times C restricted on T applied on G contracted by S. So this is because we know how the coproduct is determined. So the type of F is the integer composition determined by the size of each SI. So with the notion of these F values, we have the notion of quadrisymmetric invariance. So indeed, this is another polynomial, or another sum, but we want to describe this by a vector, a F, or we call it flag F vectors. And this vector is indexed by integer compositions of alpha, such that F applied on alpha and C is a sum, where the sum rounds over or the composition such that the type of the composition is alpha. So indeed, these are the coefficients of quadrisymmetric functions, firstly discussed by Argyll, Bergeron, and Sotila. So this is the function to a terminal object in the category of combinatorial Hopf algebras. And we will discuss this invariant in the setting of Hopf monoids and discuss the coefficients. Okay, so first we have a nice result with respect to this quadrisymmetric invariant. So if the character C is odd, then for any x, this flag F vector satisfying the Bayer-Bellera or generalized dense Somerville relations. So these relations discuss a flag vector for the order complex from a Eulerian poset. So we have the similar result on odd characters of Hopf monoids. So indeed, we may ask a question, whether there exists a polytope or a Eulerian poset whose flag F vector coincide with our flag F vectors from the Hopf monoids. So indeed, there's a nice answer for phi prime on the Hopf monoid of convex geometries, but there are many things to explore. So let's discuss what's happening here. So to introduce this, I don't want to read this sentence. I just want to use this example to describe what this sentence discusses. So first, we have a convex geometries, G, and we use this 3 collinear points example. And then from here, we can construct a lattice. And we only consider the proper part of the lattice. And from this lattice, we consider the order complex of these proper parts. Then we're able to get a subcomplex of the Coxeter complex. So here, this is the subcomplex we obtain from the convex geometry of 3 collinear points. Then nice things happens on the quadrisymmetric invariants. So first, the F vectors corresponding to eta enumerates the faces in this order complex, all the faces. And the F vectors associated to zeta enumerates faces in the interior of this order complex. So which means we don't care about what's happened on the boundary, but we count everything happens inside. Okay, and finally, we have where the Bayer-Bellera relations happens. So to do this, we use a colored simplicial sphere structure introduced by Bellera, Shaw, and Proben. So we used G as a convex geometry on I, and then by these 3 authors, we could construct a Eulerian poset. So here, this is our example of G. This is the order, this is the lattice, and then this is our Eulerian poset. So actually, I did not include the maximal element in this poset. So mainly we care about what's happening in the middle. Okay, so indeed this poset is determined by extreme values of the convex geometries. So from this Eulerian poset, we can determine a CW sphere. So this is not simplicial, but this is only a CW sphere. And then we could able to obtain another order complex by doing the barycentric subdivision of the CW sphere. So this result is nice because we indeed have a colored simplicial sphere in which the Bayer-Bellera relations happens on the F vectors, flag F vectors. Okay, so the nice result from our quadrisymmetric invariance on Hopf monoids is this flag F vectors corresponding associated with phi prime on G actually enumerates the faces in the links of the vertex in the order complex. So we draw the pictures here, and the link is corresponding bounded by the green spheres. So indeed, we have 4 green spheres. And this also corresponding to the face set of the CW sphere. So which is here, we have 4 face set. So here I computed the flag F vectors from the Hopf monoids. So they satisfy the Bayer-Bellera relations, but more importantly, we have a nice geometric description of this flag F vectors, which means we coincide or we connect this result of flag F vectors from Beyer-Galeras to the result from the Hopf monoid structures. Okay, so I think that's all of the materials today.
Let's thank E10 for that lovely talk. Does anyone have any questions they'd like to ask her?
I have a couple. So the first thing is okay, I guess first, very nice talk. Secondly, I realized I had a little bit of trouble following the middle because even though I've worked in this area, I named all of my characters differently. And so getting used to the other notation was tricky, but the Ada character is just one on all the basis elements, right?
Uh-huh.
And then the Zeta character was the inverse of that?
The inverse of eta bar. So
okay, so that an eta bar is one on basis elements with even base set and -1 on basis elements with odd base set.
Are you talking about zeta? Or
sorry, so eta bar.
Oh yeah, eta, yes,
yeah,
yes.
Okay, and so that's the odd character or whatever. Okay, yeah, sorry, this always gets me because Stanley uses zeta for the all ones character whenever he's defining the Mobius function, and it always bothers me that this is not
yeah, so this
the same here.
Yeah,
like
yeah.
it really feels like Ada should be named.
Okay.
That's more of a rant than a question. I wanted to make sure I had my characters right, but I guess my real question is that, so it feels like a lot of what we're doing here is we are avoiding having to compute the antipode of the monoid in order to come up with our reciprocity theorems. Like that's what we're using these odd character formulations for, so we don't actually have to compute an antipode in order to come up with a reciprocity theorem.
Yes. So because we don't know the cancellation free formula for the convex geometries. So
right.
Yeah, this is the main issue.
Yeah, that I had a feeling that was the case because my academic sibling had looked into that and I was like, wait, we found it? No, okay. We found a way to end run it.
There's a question in the chat that I want to read out to you. It says, nice talk. Have you worked on the antipode formula for Hopf monoids of posets and complex geometries? Are these Hopf monoids can be realized as sub-Hopf monoids of the generalized commutohedron Hopf monoid?
Okay, so on the poset, we know the answer. So Marcelo Arguer, who's my advisor, has a paper on Hopf monoids of generalized commutohedra, and he discussed some nice description on the antipodes on the poset. I also have a different description on the poset, so on the cancellation free formula of the poset. So actually for poset, we can answer this question. So indeed, the coefficient of the antipode corresponds to what is covered, the cover relationship in the partial orders. But for convex geometries, we don't know. So we know the general expression. So by Takeuchi's formula, there's a formula named by Takeuchi, and this helps us to compute any antipode. But this is very general, so we don't know what happens on the cancellation free formula for convex geometries. Yes, and I think for the second question, it is discussed in the Marcelo's paper. So
Yeah, in the GP paper, it talks about the inclusion from the poset monoid into GP.
Yeah.
I assume convex geometries can be embedded as generalized Bermuda
No, because the rank function is not submodule, which makes things very bad.
Mhm.
There are no more questions at this moment. Let's thank Yichen one more time. Maybe we'll stop the recording and go into our secret question time.